Testing 1, 2, 3. Okey-dokey. Okay, let's see. Almost ready to go, guys. Let's see. Okay. I think that's sort of looking at me now. So anyway. Live transcription is on. Now let us see. I must share screen. Don't view. Slideshow. Slideshow. Let's see how this works. Ah, yes, very good. No, but that's not what I want, is it? Slideshow. Primary monitor. Okay. All right, let's go with this. So, somebody told me, hello, Snigdha, how are you? Somebody tell me what it's like to be a college student. What it's like to be your age. Because I do not remember.
You wake up after 8 hours of sleep and you're still tired.
No, that never changes. Stressful / hard. It's hard, haha, yeah, okay, all right. Numb, okay, that's probably better than other alternatives. That's what I'm planning to be later tonight after eventful. Yeah. So how is it? You get 8 hours. Yeah, oh my gosh. So much coffee with urge of learning. Elvin, good. In theory. Okay. Yeah. No, it's funny. Some people, they adapt themselves to a few hours, you know, like 5 or 6 hours, and you know. And I think some people also have a little bit deeper sleeps, you know. But you know, I don't think it's a good thing to talk about sleep this late in the day because my face is going to hit the keyboard. Yes, there's still more to be done. I actually dreamed of having a job where I could just forget about it when it was over, but that never happened. Anyway, so let's talk about method validation today. All righty, share this whole screen here. All right. So no, I call this method validation, right? And another name is quality assurance. It's basically just making sure that what you're measuring is what you think it is. Let's see, 1, 2, 5, 22 people. That's not too bad. It's not too bad. Only one picture, however. I only have one. You know, there's a bunch of names. Nobody looks live, but I'm just gonna presume that the people who are there are alive, and I will pick on you one by one. We'll see how that goes. See how much y'all hate me by the time we're done. We're just gonna see how much you'd learn to hate me. All right. So basics, method validation, standard additions, and internal standards. So these are these are just concepts. This is actually quality assurance and method validation are conceptual things, actually. And they're not actually quantitative mathematical things, although they connect to mathematics. Okay, so an example, actually this is from, I think it was in Fremont. There was a crime lab and they were analyzing cocaine and they had thousands of samples, all in a big backlog. And the analyst was completely overwhelmed and probably was using the product. So it was pretty bad. I think this is where Harris got this, right? Or whoever wrote this Chem Ed article got this idea, right? So, you know, how do you determine if a mistake was made in an assay? And, you know, I don't know if those mistakes are intentional. I don't know exactly how to do that, but it's an interesting article on that idea. And that comes into quality assurance. So quality assurance is getting the right answer. You know, it's the same as method validation, is how do we make sure our answer is accurate and precise. And you know, accuracy is dependent on the answer that you need. So you need to have in mind the answer that you're trying to get when you address the question of accuracy. And there's generally no point in getting a more accurate answer than is necessary. So for example, if you need to know that the iron levels in tap water are below 10 parts per million, if you get 3 or 1 or 2, it doesn't make any difference what the next digit is. You know, it doesn't matter if it's 1.1 or 1.2. If it's 1, then it's okay, right? But you do need to know that the 1 is accurate, right? And it boils down to get the right data, get the data right, and keep the data right. So, one of the things you can do is you can write use objectives. So how are you going to use the results? What will you conclude based on the results? And you can write these so-called use objectives, right? And then how good do the numbers have to be? That's called a specification. And then you have to choose the method that you're going to employ to meet that specification. So for example, you can get a yes, no on many metals using a colorimetric test. Is it present at above, 100 parts per million or something, or 10 parts per million, just on a colorimetric test. And that's where you would, mix in some dye molecule and see the color that develops, right? But it's not going to tell you, if it's there at half that value or etc. So you need to choose a method, maybe ICP or something like that, that will tell you with the precision and accuracy that you need whether or not that method is good enough. Okay. And when you're done, you assess what you've done, compare with results specifications, maybe do a t-test, document the procedures, keep records where suitable. Okay. The goal of quality assurance is making sure that results meet the customer's needs. Customer could be the government, or it could be the public, or it could be a client in a lawsuit, or the Environmental Protection Agency, for example. And so after you've written the use objectives, you have to keep in mind that the raw data or the measurements, the treated data are the concentrations derived from the raw data by use of the calibration, right? And the results are the quantities reported after the statistical analysis of the treated data. And we're going through all three of these in our first and second long experiments, which we'll be starting on Wednesday. So, for example, those of you who are going to be here on Wednesday, could I see a show of hands for people who have the Wednesday lab? Excellent, excellent, excellent. So we'll see all of you on Wednesday, and we're going to do the first long lab, which is HPLC. All right, cool. Now, so specifications. They determine a lot of the answers to a lot of the following questions. How should the samples be taken? So, for example, for HPLC, we'll buy a case of Diet Coke, and we'll take probably 2 or 3 cans per lab section, and we'll analyze them. We'll keep track of what can is which, and we'll get an answer that we can compare can to can if we want to. That is, that we will compare can to can. Getting this transcription right. So how many are needed? You know, what kind of statistical certainty do we need? Are there precautions needed to avoid degradation? In this case, yes, we have to open them and use them in the same day. What are the practical restraints? Time is the main one in this case, because we have plenty of standards, we have plenty of mobile phase, but we have to get through our analysis within 3 hours. So we have to come more or less prepared. What level of accuracy will satisfy our use objectives? Well, in this case, our accuracy target is about 1 part per million, or 1 milligram of caffeine or benzoic acid per can. And what rate of false negatives or positives is acceptable? That doesn't really apply to this case since we're going for a quantitative analysis. And what is a positive, false positive, or negative? Well, false positive is, for example, if it's a pregnancy test and the test says you're pregnant, but you're not, but reality says you're not, I guess you would say, then that is a false positive test. False negative test is if the pregnancy test says you're not pregnant, but you have a baby, right? And there's actually some interesting cases that you can think about when even a low false positive or false negative rate can significantly change the outcome of a particular analysis. So, for example, let me just going to go to a little whiteboard. Okay, screen share. Whiteboard. We can think of a case where we have, say, a low frequency disease or a low frequency condition. Let's say, could be what sort of a rare but scary disease. Say it's lupus. Say you can have a test for lupus. And lupus is a weird autoimmune disease that can be pretty devastating. But it's not common, right? It's and an important thing to know is the frequency of lupus in the population, actually. So let's say that we know that the incidence of lupus is 1 out of every 1,000 people. Maybe has lupus, right? And this is called the prior, right? And let's say your test will give 1 false positive out of every 100 tests, right? So then you may ask, well, if you test positive, what is the likelihood that you actually have lupus, right? Well, if you take this hypothetical sample of 1,000 people, right? And you're going to say that there's 1 true positive in there, but the false positive rate is 1 per 100. That means that there are going to be, oops, that's scary / weird. Anyway, that there are actually going to be, let's make this a box with a plus in it, right? Then there are also going to be 9 other false positives. So your there will be 10 positives roughly, and only 1 true positive, right? So in this case, your positive test for lupus means that you have a 10% chance of having lupus, roughly. Does that make sense to everybody? Do y'all watch Veritasium? Does that show of hands for anybody who watches Veritasium? Morsal, yeah. Did you see the Bayesian Veritasium, Morsal?
Yeah, I used to watch his channel a lot back in the day.
I know. I just absolutely love that. Recently he kind of overinterpreted this thing called the pointing vector,
Hmm.
and he sort of overly broadly concluded that electricity doesn't travel through wires.
I liked some of his older videos better. The newer ones seem kind of commercialized. That's why I watch like Nile Red instead.
Oh, I love Nile Red.
That guy's funny.
He is so dogged. He is so determined. And I love the one he did on making superconductors, because you can just see all the mistakes he made and all the problems he had. It was lovely to see how difficult that was, wasn't it? Did you see that one?
The conductors one? No, I
Ah,
saw a different one where this is for Nile Red, right? I think he had something else, but it wasn't like a conductor, it was something different.
oh, okay. All right. Yeah, I've seen a couple. The only one that comes to mind right now is the superconductor one. Anyhow, I digress. I happily digress. Let's see here. Let me get a new. I'm going to put this to bed and then get a new share. Let's see. All right. So that's sort of a little detour into false positives and false negatives. So, you know, for example, here in a cancer test, right? Out of close to 1 million people with healthy people that were correctly identified as being cancer-free, 10,000, that's 1 in 100, were false positives, and 2,000 were positives, were true positives, and there were only 20 false negatives, right? So false positives and false negatives, and then, I'm sorry, false negatives here and false positives here. So there were a lot of false positives. So if it were a cancer screening, what would you prefer, false positive or false negative?
Positive.
Yeah, me too. Me too. Even though it would be scary as shit, I would rather, you know, go in for a biopsy, you know, and have them put me through everything and say, oh, no, you don't have cancer. Get out of here, kid, you know? Then actually like have like a false negative and think, oh, I'm fine, and then drop dead, you know? Does anybody disagree with me there? Does anyone not want to discuss cancer anymore? Okay, I'll shut up. Okay. All right, so they're just a fact of life, you know, that's true for any sort of process. Oh, yeah, awesome. So people are answering in the chat. I'm sorry, I don't. Oh, oh yeah, Tuesday, the Morsal Tuesday lab. You just come in tomorrow and we're going to do lab 0. We're going to do the UV Vis lab. So a couple of groups have already done that. Wednesday and Thursday have done that. And so you guys are going to do lab experiment 0, the extinction spectrum of crystal violet. Excellent. Okay. Icky dicky. So sorry. So let's get a little bit more vocabulary here. Selectivity. Now this is focused down a little bit more into the weeds of analytical chemistry anyway. Selectivity is your ability, or the instruments or the method's ability, to distinguish an analyte, which is the chemical in question, from other species in the sample. So other things in the sample, right? And so if it's selective against interference. Okay. And sensitivity is the ability, is really the response to changes in analyte concentration. It's the slope of the calibration curve. All right, now how about a blank, right? Hopefully your blank does not contain analyte, right? It's not supposed to. And there are certain cases in mass spectrometry where your blank will contain a known fraction of analyte. That is, your blank will contain a known fraction of analyte. Okay, analyte. And I liked, it said. Okay, so for our purposes, blanks will not contain analyte, but they may contain interferences. So if your interferent is present in the blank, then that's good, because that will tell you how that same interferent will be affecting your analytical signal. It may also account for trace amounts of analyte found in the reagents. That's where a method blank comes in. Right, and then if you go back to your blank occasionally, you can see if analyte from previous samples are being carried through. So this is maybe typical of a flowing system like an HPLC or an ICP, or something where the sample goes in as a liquid, and it might stick to the tubing and might be present, So sometimes you have to bring back the blank. And, and then you have a special blank that has all the chemicals, but not the sample. Oops. Okay. So a method blank is something that we use in the MIP, experiment number 2. We also use spike recovery, which we'll talk about later today. Okay. So again, a method blank has all the components except the analyte. It's taken through all steps of the analytical procedure. And you can, if you want to, subtract the response of the method blank from the sample before calculating the quantity of the analyte. Now, I would not necessarily do this because it can also give you a spurious or a negative concentration. So ideally it should be very small, right? In which case subtracting it probably won't make a difference, but in any case, a reagent blank, you can just prepare a blank, not necessarily going through all the method blank procedures, right? Then a field blank can indicate if an analyte is inadvertently picked up by exposure to field conditions, right? So this is a good one for the forensics folks, right? Because field blanks are not that uncommon in crime scene analysis. Because if you're doing a real sensitive method, like a DNA method, sometimes you need to go to your sample area with duplicates of your sample bags, right? And you open the sample bags and you let them be exposed to the environment, and then you close them and you take them back. Or you can take them, open them, and maybe put a blank object in them, or an object that you know should not have the perpetrator's DNA on it, and put that in the bag. And then you can show if that comes up negative for the DNA, then that supports your conclusion if you get a positive or a negative. So, that's just for the forensics folks. And you guys want to hear a little story? Anybody?
Sure.
Okay, cool. So you may have heard this, Catherine. I don't know if I told this, but there's an interesting book. No, this is not from the book. This is just from a story I heard on the news. There was a case from Texas where a young lady was convicted of killing her husband by poisoning him with arsenic. And the case went to trial, and the lady was convicted and jailed. And sometime later, this guy who he was an analyst of some sort, and she did she put in the orange juice? No, she did not actually. The thing that happened to her, right, was that she reacted oddly to her husband's death, right? Her husband died sort of unexpectedly. He came back from Iraq, and they were reunited briefly, and then he died. And then the wife, I don't know, maybe there was some insurance or something, but just fairly shortly after he died, she got breast implants, and for some reason that was maybe suspicious to some law enforcement person, right? And they pursued her and said, hey, what's up? What, did you kill your husband? And she said, no, what are you talking about? And they took the corpse and they had it analyzed by a lab to look for arsenic, right? They looked for a variety of toxins, and one of them was arsenic, I guess. And they found arsenic everywhere in his body, just in the brain and the stomach and the tissues, the hair, everything, and I thought, oh my God, this lady, she really poisoned this guy super bad, right? But the guy who noticed this in the news, he was from a different state. but it came up in the news and he said, hey, this is not typical of arsenic poisoning. You know, it's normally localized in the stomach and like somewhere else, but it's rarely found all over the body, you know? So he looked into this case, and long story short, he discovered that the forensic lab in question did not run a proper blank, right? The blank is the thing that it tells you what, yeah, exactly. Oh no. And this lady was in jail already, you know? And if it hadn't been for this Good Samaritan, she'd probably still be there. But it just, you know, in fact, the lab was pretty bad. There was arsenic all over the lab, you know, and they found it in a lot of samples from the lab. So it was just an analytical issue that nobody caught. And, you know, whoever the lab techs were there, they, you know, they were really sloppy. And it just something that a story that I like to tell because it emphasizes the importance of running a blank, you know. Anyhow, so that kind of a blank, that's just almost any blank would help there. A reagent blank or a method blank or a field blank, any of those three could have caught this fact that there was arsenic. Yeah, and it was a super messy lab apparently. You know, it's they might have gotten some volatile arsenic. That's for example, there's the trihydride, arsenic trihydride is volatile. Yeah, probably a few OSHA violations there too. Yeah. And I don't know what happened to the scientists. I'll Google it. You know, you guys can Google it afterwards, and hopefully it's a true story. I'm pretty sure it is because I've told it a bunch of times and I've been fact checked a bunch of times. But interesting story. Hopefully I got it mostly right. But it's an example of how blanks are important. And there's also an interesting book called The Poisoner's Handbook. I think I might have mentioned this earlier, but the Poisoner's Handbook talks about the detection of poisons in people, and it's set in Prohibition era New York, and it's really a fascinating book. But anyway, Poisoner's Handbook, you want to look that one up. Okay, moving on here. Spike recovery, we were going to do this in the MIP experiment too. Experiment 2. And the spike recovery tries, it's not perfect, but it can, oh yeah, Cynthia Summer, yeah. So the spike recovery can, it's analyte, right? A spike is analyte that you intentionally add to the sample in a known amount and take it through the entire sample preparation. And then at the end, if you have samples without the spike and samples with the spike, you can tell if the entire spike is represented. So, for example, in the MIP experiment, we're going to add like 8 milligrams of iron to our tablet. Right at the time we dissolve it, we're going to spike it with 8 milligrams of iron. Then we're going to do 2 other tablets with 0 milligrams of spike. Right? And when we're done, we're going to take the average of the spiked and the unspiked, and we'll see how much iron makes it through this analysis, right? And sometimes there are other components which can either mask the analyte response, or you can lose analyte, or there's something that may increase the analyte response, right? So it's, this is, to me, what this does is it indicates if you have problems of contamination or loss in the sample preparation step. Right, so spike recovery validates the sample preparation. All righty. So we're going to do this in the lab, and that'll be experiment 3. So that will actually be, it's coming right up, because we're only going to dedicate 1 week to HPLC, maybe 2 lab periods to it, because we're going to do it, and then we want to spend a little time analyzing the results. But yeah. So and when you compute spike recovery, you talk about percent recovery, and so it's the so it's the concentration in the spike sample minus the concentration in the unspiked sample, right? Divided by the size of the spike, right? So this could be like 26 milligrams minus 18 milligrams divided by 8 milligrams, right? Which if you spiked with 8, then and you this would be 100% recovery, right? Because 26 minus 18 is 8, and then if you divide that by 8, you get 100%. So in any case, it's fairly straightforward, So you can do it in concentration terms as well, and that works just fine. In this case, you would say, well, you would take the number of micrograms in the spike solution and divide that by the volume of sample solution that is represented up here. Okay, and we'll just see what we get. It's hard to predict. I'm hoping that our answers are going to be pretty close this time, because I did a bunch of work to try to get our data as nearly perfect as possible. So we'll see. So okay, so if our fortified sample gave 15.3, then basically we would just take 10 and divide by 5. And then times 100%. And that equals, I don't know, something they'll show us on the next page, I think. Anyway, that's fairly straightforward, right? That's going to be 5.3 over 5. That's 106%. Okay, so now we are going to start. Thank you, Snigdha. Excellent. So when we're going to start to approach the large number of samples regime. And our last instrument, we had a beautiful ICP, but it died, unfortunately. Died, and or maybe it was just lame and Mike Stevens shot it. Kind of like the 4 horses in the horse hospital. Have you guys know that? Like if a horse breaks a leg, it's extremely difficult to get it back to life, you know, because their legs are actually kind of delicate. Anyway, so the horse hospital, the either you have a broken leg and you're going to die, or not. So I think the ICP might have had a broken leg, but it had a nice sample auto sampler. And there were, sometimes we would stack up 3 groups, and there would be 5 samples. Yeah, there would be 2 spiked, 2 unspiked, and a method blank. Then there would be 6 standard, so it'd be 11 measurements per group times 3, that'd be 33 measurements. And there could be some significant drift between the beginning of the standards and the end. And so we might we might see a little bit of this. And there's temperature, but with the MIP that we're using, the most likely candidate here is the peristaltic pump. And you guys will see it, and it's common on all these $500,000 instruments. It's just a little stupid, cheap pump, and it relies on flexible tubing, and the tubing it's put between rollers, and it has to expand when the roller kind of gets over it, and that sucks in the stuff, sucks in the analyte solution, and then the analyte solution gets pushed through the tube by these rollers and creates a little pulsed flow. And they are just not reliable, but they are still used on very sensitive analytical equipment. And don't ask me why. I'm not a chemical engineer, but there must be a better way. Anyhow, if the peristaltic pump changes speed, like for example, if you do all your standards and it's giving you 1 mil per minute, then you run your samples and it's somehow running at 5 mils per minute. I'm sorry, 0.5 mils per minute. So it's gone down by a factor of 5, or a factor of 2 rather. Shut up, Roger. It's gone down by a factor of 2 when you run your samples relative to your standards. Then you won't know that, and the samples will look like they have half as much analyte as they were supposed to have. And so that's a form of method drift, right? And there's a way to get around that, which is called internal standard. Oops, sorry. which is called internal standardization. And using an internal standard is one way that you can do this. And an internal standard is useful when you have an instrument that can measure on any of, on a number of non-interfering channels. So for an ICP, you've got hundreds of different wavelengths that you can monitor on, you know. And what you can do is you can put in a rare element in a known concentration in your sample standards and your blanks. And then at each measurement, you monitor the internal standard concentration. And it should be the same in everything, right? But if it goes up or down, then you know that something is changing with the instrument response. And it's a red flag, right? It's not normally something you'd use quantitatively, but you can if you want to. So, we'll talk more about what an internal standard is when we get to ICP, right? Then you can also do calibration checks, or you can also do validation standards, right? If you use a different calibration solution, then this is called a validation standard. Right, a validation standard is it's supposed to be the same as the calibration, and if it's not, then something's wrong. Either the calibration standards are off, or the instrument's off, or both, right? So that's another red flag, right? So a red flag for the internal standard, for the validation standard. Actually, I'm gonna go ahead. Oops. I'm good at squeezing these things here. I'm gonna write here properly. The red flag will be in the internal standard, will be off. And then the calibration check, this will be this can, if you don't have an internal standard, you can just rerun a calibration standard here, and this will be the validation standard. You can do quality control samples, right? These are actually samples that have gone through the whole step. So these are prepared samples. All right. How's my audio, guys? Is it okay? Yeah. Okay. Good. Thank you. My computer's trying to tell me that my audio may be bad, so and it has been on occasion with this computer. And the then a standard operating procedure is just like it's just a set of rules to follow, you know, to make sure everything is standardized. Okie dokie. All righty. So lastly, we can think about assessment, you know, documentation, etc. And if in the end the use objectives are met by your procedure, then the method is fit for purpose. Okay, so I've never done this, but it's a helpful thing to do, and it's an interesting example because if you run a standard periodically, it should fall within a certain range of these control of a control standard plot here, right? And in this case, they have a mu plus or minus 2 and 3 sigma indicated here, and they show the control line drifting downward here, and now it's outside of 2 sigma, so that's a warning that the method can be going haywire. So 95% should stay within 2 sigma, right? So that means 1 in 20 can be outside. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 20. So there's 20, there's probably 40 samples here. So this is actually almost to be expected in this many samples. But if the next one or the next one are outside, then you would have to shut down this method and fix it. If this is if this is important to your process. Okay. It's lanthanum in uranium as a part of the non-proliferation treaty. Micrograms per gram. So this is parts per million. Parts per million lanthanum in uranium. That's probably pretty common. Okay. And then there are standard methods that should give reproducible results, right? There's American Public Health Association, AOAC, that's the official Association of Official Analytical Chemists. Oh my God. ASTM, American Society for Testing and Manufacturing, and the NIOSH monitoring, and many others, OSHA, EPA, FDA, USP. Okay. So we'll just go on for a little bit longer, and then I will finish up today fairly shortly. But as I've been saying, the method validation, it's a way of offering proof, right? And I wouldn't actually say proving. I would say it was proving beyond a reasonable doubt, maybe. It's the offering of proof that an analytical method is suitable for an intended purpose. Things depend on the presence, the existence of standards with a known concentration, for example, and it's possible to find some chinks in the armor here, but what you can do is you can put together a set of independent analyses and maybe some independent standards and whatnot that can get you within, say, 1% or a part per thousand or a part per million of the likely truth here, right? And then, however much accuracy you ultimately need is probably way less than that. And in that case, you're proving that your method is acceptable, right? And the various criteria are selectivity, meaning that you see analyte and non-interference. Linearity, that kind of speaks for itself, but the concentration and signal are proportional. Right? Accuracy and precision. You can state what they are. The range, the high to the low to the high. The limit of detection and the limit of quantitation. And then the robustness is if other factors in the lab change, other non-critical factors change, does the analytical result respond? So you could say resistance to perturbation. That's perturbation here. By environmental factors, let's say. Okay. And we will talk about more of these. So selective and specific are the same thing. And chromatogram here is an excellent example where you can sort of see visually the selectivity of a method. And sometimes it has some surprises for you, but again, if you know your standard is pure, then you can go further in establishing the purity of your samples in this way. Okay, so in a chromatogram here, we have absorbance signal. This is the absorbance of light by the analytes that travel through a column. And the idea is that the analytes have a different transit time through the column depending on how strongly they interact with the stationary phase in the column with the usually there's a sort of a powder that's packed in the column, and then the liquid flows by it, and the different chemicals have a different affinity for the non-moving phase, the stationary phase, and their progress through the column is retarded and they come out later, right? So when things are working well, things come out in individual bands. So there's 1, 2, 3, 4, 5, 6, 7. Oops, there's 8, there's 9, right? And so in this case, you could say that if we know how much of this is in a sample and a standard, if we know, if we have a known standard and a known sample, then we could establish the fact that this analytical method can distinguish analyte from everything else in the sample, right? From all these other components, because they come out at different retention times, right? So How we doing? Okay. I know it's probably pretty boring, but you guys are doing good. Thank you, Catherine. Everyone else is asleep, I think. Oh, God. So linearity, blah, blah, blah. Okay. So I think I'm going to leave it off here, right? Probably yammered on long enough. So Tuesday, folks, please come in tomorrow morning at 9, and we will do our crystal violet experiment 0. And if you want to get prepared in advance, you can figure out how to produce a 1 micromolar solution of crystal violet in water using no more than about 40 mils of solution. There's no actual pre-lab, but I want you to read the lab beforehand so that you kind of have an idea of what's coming. And if you do, then you can get out early, and that'll be awesome for all concerned. So designing. So are we designing our experiments for tomorrow? And is there a pre-lab? There's not a pre-lab, but we are sort of designing our experiment tomorrow. What I'm going to have you do is figure out how to prepare a 1 micromolar solution of crystal violet. Then you have to tell me that back in your report, right? So you're going to have to sit down and figure out how to take this 408 gram per mole dye, dissolve it in water, and maybe dilute it such that it is about 1 micromolar. And then for experiment 1, actually, Anne, we are. It's much easier this semester. We are not. I'm not going to have folks design their own spreadsheets because I don't know. It was too chaotic for me. So I have created the spreadsheets for you, and you guys are going to more or less follow instructions for experiments 1 and 2. I mean, you'll get different answers and you'll have to put them together into a spreadsheet, but the structure of the spreadsheet will be the same for everybody. And then you'll be graded on the interpretation. But anyhow, I guess that's here nor there. Yeah, so just figure out how to make a 1 micromolar solution. So, it's basically, I don't want you to use a whole lot of dye or too little dye or too much water or too little water because there's problems with all those cases, right? Oh yeah, and I'll work with you until you get the right answer, and then you do it. It only takes, 20 minutes at the most. So, all righty, guys. Are we ready to sign off tonight? Is it Miller time for Roger?
For those of us in the Wednesday morning lab, is there a pre-lab that we have to prepare for experiment 1?
No, but do look through the lab. I'll have everything ready. I'll have your Coke. I'll have your standards ready, and you guys are just going to come in ready to sort of perform it. We'll talk about it, but read through it so you have some idea, maybe some questions.
Okay, thank you.
Thank you.
For Wednesday's lab, do we need to have the crystal violet report finished by Wednesday?
Oh, right. Yeah, I think so. Let me, I have to check on the lab report due dates, and I'm gonna set them up tonight. So plan on having your first lab report done by tomorrow night, or by Wednesday night, rather.
Okay, thank you.
Okay, and if you have questions, just let me know, because I can answer questions, just not too far after. Okay. All righty.
Okay, sounds good. Thank you.
Okie doke. Thanks. Okay, guys. We will see you all very soon.